welcome Tom Bujok.
Thank you very much. Is it working? It's working. Okay. Good morning, everyone. I'm happy that you joined this session. I really appreciate it. I was wondering today in the morning whether it's fortunate or unfortunate that I have a session, the first session in the morning after the great JFocus party, because it would be fortunate if you all, partied till late and got totally wasted, because I could tell you a bunch of lies, but you wouldn't be woken up enough, to understand it, so it would be good for me. It would be unfortunate if it was only me who partied till late and got wasted. To give me some hope and to wake you up, could you raise your hand if you partied till late and got wasted? Oops. Okay, anyway. So, my name is Tom. I work for Hazelcast. You can find me on Twitter under Tom Bujok, and you can also visit my blog under reficio.org. You can know me because I work for Hazelcast, and I also created like a Windows shell called Babun. I don't know if you know it. You can have a look at it. Yep, so you may think it's going to be another NoSQL talk, right? NoSQL databases are there for a couple of years right now, but it's like it's a world of benchmarks and tutorials and certifications and conference tracks and even separate conferences. But if you type NoSQL in Google, there's going to be a salesman that will call you, right away, even without giving your phone number, because it's such a kind of, like a brutal marketing world. So in this world full of buzzwords, it's actually very, very easy to lose the focus. Why do we actually need NoSQL databases? What are the main characteristics? Why we actually need them? So during this session, we'll try to kind of, have an overview, like from 10,000 feet, we'll try to have a look at the NoSQL solutions. We'll try to have a look at the main characteristics of the NoSQL databases, and we'll also try to compare them to, like normal traditional RDBMS databases in order to, see and in order to understand why we would need one. So the first thing is, I don't know if you see a difference between these two pictures, like from 2005 and 2013. It was taken during the Pope elections in Vatican. And as you can see, in 2005, we barely see any smartphones or digital cameras. But in 2013, you see like everybody's holding a smartphone on a tablet. And what do you think they are doing with these pictures or videos or audio recordings that they have made? Obviously, they're posting it on Twitter or Instagram or Facebook or Google Plus or mailing it somewhere. So you see, even from this picture, you can see that the way we're using the internet has changed rapidly. Like before, like at the beginning of the 20th century or 21st century, we were mainly consuming the data. We were reading sites, we were reading blogs, we were reading news feeds and stuff like this. And but it has changed in a way that now we publish a lot. We publish much more than we actually can consume. And I really like this chart from DYNAMO. This is, I think, from 2014, so it's already outdated by far. But you can see that, for example, on you have like 277,000 tweets every minute happening, or you have like 400 or 16,000 Tinder user swipes. I don't know what it is, but whatever. You have like 4 million Google searches every minute. So you can see there's a lot of happening. It's a huge web scale that's going up there, and there's like 2.4 billion people using the internet every minute of the day. So in order to handle such a traffic, you need to change your architecture a bit, because otherwise you wouldn't be able to handle it. What does it actually mean for Facebook? What such a scale means for Facebook? It means that they have 1 billion of daily active users each day, and this is from April 2015, so it's also outdated. And by the way, they do not really publish such data. It's very difficult to find this, but yeah, it shows the scale. So they have like 600 terabytes of daily asynchronous replication of data between data centers. So you see it's a humongous amount of data. They are storing like 300 or more petabytes in total, or like in total data. So you see, and this is from April 2014, so you can already see this is probably it's much more. But the most interesting thing for us, it's like they are handling billions of queries per second. So can you imagine how can you create like a system that is handling billions of queries per second? And the first question that we want to ask today is, okay, so we want to handle a billion of queries a second, and can our traditional RDBMS, so relational databases, can they handle it? Is it easy and is it possible to create such a system using an RDBMS? And in order to answer this question, let us have a look. So, what it means to use an RDBMS? It means that we have a relational database, a relational model. We have to model all our data up front. We have all these relations, and we also have ACID, which is kind of the core building block of each relational database. So we've got atomicity, consistency, isolation, and durability. I'm not going to go into the details because you know it pretty well, all of you. But knowing that and having that in mind, what kind of problems can we face when we use RDBMS system to handle the famous or infamous web scale? The first problem is with scaling. So everybody shows this picture. How can we scale our application? The first way how we can scale our application is to scale up, meaning that we can add some processor, we can add some hard disk, we can kind of buy a more powerful server, but there's always a limit, right? You can't add processors like in an unlimited way, or you can't add memory in an unlimited way. There's always a limit. So the huge hype now is about scaling out, meaning that we're going to use commodity hardware, we're going to use cheaper servers, but we're going to use a lot of them, and we're going to scale out. So we're going to have servers in different locations. We're going to do the sharding, and we're going to store some data on each server in order to load balance the load and in order to scale. The other problem that we can face is how can we actually do sharding and partitioning with an RDBMS? Is it easy to achieve? Is it like a building block of an RDBMS database? So let's say imagine that we have 3 servers or even like 2 servers, and we store some data on one server, or some data on the other server, and we want to do a join because there's like a referential integrity between these servers. Do you think it's going to be quick if the data are located in 2 different data centers? Of course not. These are problems that you would normally face if you wanted to do referential integrity in a distributed manner among a couple of data centers, or even among a couple of data servers that are located maybe not in the same server room, meaning that the latency is going to increase rapidly. So this is another problem that we may face. The first problem that we may face is a transaction, because when we are using RDBMS, it's all about consistency, right? So when we write to this table and we want to write to the other table and we want to do it in a consistent way, we are opening or firing a transaction, we are changing some stuff, modifying some stuff, and then we are committing the transaction. So you can already see what happens, and we have this distributed transaction spec, right? We have even like 2-phase commit that we can use when we have a couple of databases and a couple of data servers and that we want to modify it at once. So you can see already with 3 nodes, it's getting a bit complex, what kind of messages have to be passed in order to commit like a distributed transaction. So imagine now that you have 100 servers or 1,000 servers. Do you think it's going to scale? Do you think it's going to be, your throughput won't be harmed by the fact that we're opening the transactions, locking some tables at, let's say, 20 servers that are at distant locations? This is obviously a problem that you would face if you use transactions in a distributed manner with a lot of databases. So that's the next problem, and the last problem that I want to have a look at is related to replication, because if you are handling web scale, if you are handling users, you are handling a huge traffic, humongous traffic. We want to replicate our data. We don't want to lose our data. Like a lot of companies have been closed because of the fact that they lost their data. So we want to be safe. We want to do replication. So if we're having that in mind, that we have consistency, that we have all the constraints that we have just mentioned, how would you do the replication? If you use like the online replication, it would mean that, your latency will increase because you would have to lock your business transaction for the time being when the replication is happening, right? And when the data are replicated, then you can commit your transaction and reply to the client, meaning that the client is waiting till your data gets replicated. The other one is post-write replication, which meaning that you return an answer to your client, but then you're doing the replication, but you face some trade-offs, right? Because your replication may fail, or there may be some communication problem or network problem. You have already answered to your client. The client thinks, I'm safe, I stored my data, but the data haven't been actually successfully replicated. So this is basically things that we're going to be looking at today. These are the things that I want to show you also in the NoSQL solutions. But before that, I want to show the last thing, so the famous or infamous, again, THEOREM. And I have a question to you to wake you up again. How many of these three can we have at once? Can you raise your hands? Yeah? 2, exactly. We can have 2. But it's not as easy as that. You may hear, oh, you can easily choose 2, but hey, we are handling distributed systems, right? Which means that the partition tolerance is, like choosing P is obligatory, because in a distributed system, when you have a couple of servers, it's obvious you're going to have partitions. And by partition tolerance, in the CAP theorem, they mean that the cluster may survive communication breakages, right? So if I have a split brain situation where there's some communications problem between my servers, between my systems, I'm going to have some partitioning happening, right? So if I choose partition tolerance, I may choose one other one. Like I might choose only one that's from consistency and availability. So in the end, when we are handling like distributed systems, it's always a trade-off between consistency versus availability. If my system is partitioned, so I have 2 servers that are interconnected and I have a network problem, I can either be consistent, meaning, for example, oh, I have a partition, I noticed it, I'm not going to enable any writes to my servers because I want to be consistent. I don't know what's happening in the other server. I cannot synchronize, so I'm not going to be, I'm not going to allow any writes because I may end up in an inconsistent situation where this server has other data than the other server. Or I can choose the availability, meaning that if you can talk to a server, it may be any node of your distributed architecture, I can read and write data. If I choose availability, it means, oh, I don't care, I have a split brain situation, I know there's maybe another server somewhere there, I can't talk to it, but I'm choosing availability over consistency, which means that, I can write some row to this server, I can write some row to this server, they do not communicate. It may end up like this, that, I have a different value for the same row in this server, and I have different value in this row for in the other server. So this is basically the trade-off that you always have to have in mind. Having like a distributed system, you always have partitions, you always have a split brain situation, and your choice is then very easy. You're either going to stay consistent, so you're going to disable writing, or you're going to use some other mechanism, or you're going to choose to be available and you're going to enable writing, but then you have to handle the situation somehow when the databases connect again. So because I mentioned it, because in many situations the vendors or like programmers or architects, they tell you, oh, our database is CA, oh, our database is CP, or our database is AP. This is not really true. It may be AP in some situations, it may be CP in another situation, but it's not a binary decision, right? It's our decision. It should be our decision. We know what data we're storing, we know what data we're handling, we know what problems we may face if we have some kind of consistency problems between the tables, and we should be looking for a system that enables us to tune these features, to choose where we can choose by ourselves. If they tell us, oh, use us because we are AP or stuff like this, then the red light goes off because it should be your decision. You know your data. Yep. So looking at all we have said, right? We may say that we are handling web scale. We are having like 2,400,000 likes on Facebook every minute. How we cannot handle. We saw so many problems with transactions, integrity, and all the stuff that I have just mentioned. We can't use a relational database. We have to choose a NoSQL solution, right? That's what everybody is saying to us. So who can tell me what kind of database Facebook is using? Raise your hands. I don't see any hands. Yeah, there? What they're saying? They're using MySQL, exactly. So wait, why? What's happening? I just told you that there's so many problems with relational databases that you can't use it, and Facebook is probably like the biggest web scale application that we can imagine. And why is it possible that they use MySQL? Something's wrong with the NoSQL guys, right? Because they tell us we have to use NoSQL. That's not true, and it's always about trade-offs, and it's always about decisions, right? If you know your problems, if you know your trade-offs, if you know what you're trying to achieve, you can probably do it with any tool that's out there that's possible. But you should be really aware of the things that you're doing, or you should be really aware of the things that you're trying to achieve, and if you know them, you try to mitigate the problems, you can use anything. And with MySQL, Facebook, so they use Cassandra. I think but they abandoned it after a couple of months, or I don't know, a year or something of experimenting, and they went back to MySQL because they noticed, oh, we can't do joins, we can't do distributed joins because they'll be taking forever. So we are not doing any joins. They are also not doing any large scans, so meaning like full table scans on all the nodes because it's going to be taking forever. They also said, oh, we're going to favor read and write availability over atomicity or consistency. So the thing that I was explaining using the CAP theorem, right? I told you, oh, we have a partition tolerance, so we can either be available or we can either be consistent. And they chose availability. So they don't care, if I like something and there's a conflict because another guy liked it and somehow, my like got dropped. Anyway, you're going to get like 100 likes, so it probably doesn't matter if it's 99 likes or 100 likes. Nobody will even know the difference. They only have asynchronous replication between data centers, so they never try to be consistent. If there are some problems, they are trying to solve them, on the application level. They don't care, that if a new user joins, he's going to be seen in China, in the other data centers, maybe after 1 minute, and not instantly, because it doesn't probably matter that his Chinese friends will see him after 60 seconds. They also do not allow multi-shard transactions. So if you have a couple of shards, if you have a couple of servers, and you want to have a transactions, you are not allowed to do a distributed transaction. So this is really cool. The whole system is called TAO, and it's a data store for the social graph. There's a lot of papers, there's a lot of articles about it, so I encourage you to have a look at it because it can open, it can open our eyes what we can do with the existing technologies and also, how to solve these problems. By the way, all the people that raised their hands and answered some questions, I have some Hazelcast t-shirts as perks. So after the session, I encourage you to go to the Hazelcast booth and grab a t-shirt saying that you answered the question. Okay, so in the end we are primed, right? We may use RDBMS, we may use any technology if we know what we are trying to achieve. And right now, having that in mind, I want us to move to NoSQL. Having all the problems in mind, having all the different things that we want to configure in mind. But the huge difference between NoSQL and the RDBMS databases is that with RDBMS databases, you may achieve all the things that I have just mentioned with Facebook, right? You may do it, but it's not the building block of the database. It's not the building block of the solution. You have to do it by yourself. You have to disable joins, you have to know you can't do it, you have to, let's say, not use transactions, and you have to have all these things in your mind because, like, they are not, these databases were not designed to do such things, right? With NoSQL, it's different. They were designed, for web scale. They were designed to scale out, and so you have all these mechanisms inbuilt, right? You can use them right away. You're taking this database, you're configuring sharding, you're configuring async replication, and it's working out of the box for you. You don't have to do any special tweaks. So the first solution that I want to have a look at is Hazelcast. We're going to have a look at 4 or 5 of them. It doesn't matter which one I chose. I chose Hazelcast right now because I work for Hazelcast, so I know it pretty well. But the main goal is to look at the key value store database. And other examples are like, for example, Redis. There's a couple of them, so you may have a look at them. But the first thing I want to look at is a key value store. So Hazelcast is a bit more. It's an in-memory data grid, so you have much more than a key value store. But for now, we're going to focus on IMAP, which is like a perfect case for us when where we want to look at the key value store. So what does it mean that we have a key value store? Key value store, as you can imagine, like Java util map is a key value store. I have a key. It may be a string, it may be an integer, it may be anything, and I store something in the map under a key. It's a value. For the map, the map doesn't really care what kind of data I'm storing there. It may be a binary something, it may be like a byte array, it may be an object, it doesn't really matter. So the key characteristic here is that that the database or the solution doesn't really understand what you are storing there. It's fully transparent for the database. So that, when you store it, you just store, let's say, a blob for now, right? It's a blob, and the database doesn't understand it. We're going to go back to this later on. So with Hazelcast, it's a peer-to-peer topology. So you have all these things related to it already inbuilt that we're going to have a look later on, like partitioning and sharding. You have a topology, you have a couple of nodes. They may connect to each other. They may use TCP/IP. They may auto-discover themselves. So it's not really a problem for us to form like a topology of a couple of nodes or tens of nodes in order to scale our application. So the most important thing for us that I was mentioning, so if we want to scale, we said, oh, we have to have this scale out possibility, right? And in order to scale out, we have to shard our data. And what sharding really means? It means that I store some data on one server, and I store the other subset of the data on the other server, but it's never the same subset that I'm storing on both of the nodes, right? So that I may store all my data on all the nodes horizontally scaled, right? So you can see it in step one, we have all the data, like data are these boxes, colored boxes. We have all the data on node 1. In step 2, you can see that the node 2 appeared, it joined the cluster, so it was rebalanced, and the blue data has been migrated to the second node. And then you see in step number 3, when the third node joined, it rebalanced again, and we have like an even distribution of data on all the nodes. So we have, it's sharded, it's done by the hashing of the key, using consistent hashing, and yeah, the data are partitioned out of the box for you. So it's really easy. You just take a map that's distributed in a way. You just store your data in the map, like in Java, you just do put something, you do like 1,000 puts, and you're gonna have 300 elements on one node, 300 elements on the other node, and 300 elements on the last node. Out of the box, it's inbuilt. We're also mentioning some replication and backup problems we may have with RDBMS. In a key value store like this, replication is normally inbuilt, and you have a choice. You may do either sync replication or async replication. So you can see here that on node A, node 1, you have the red data, but it's also storing the backup of the blue data. So if the if the node number 2 goes down, the data will not be lost, because node number 1 will take over the ownership of the data, and it will redistribute them among node 1 and node 3. So this is also inbuilt, and you know, if you are more about consistency, you may choose the sync replication, which means you're going to have some latency problems, most probably, because you'll have to wait until, like, you know, your client will have to wait until the data is replicated. But if you choose async replication, okay, you may lose some backups, but on the other hand, the response time to your client will be really low, because, you know, your transaction, your put to the map will not wait for the replication to finish. And what's really cool, you can configure like the backup count. You may have one backup count, like one backup, or you may have a couple of backups. So let's say you may say, I want to store my backups on 3 nodes, right? So even if 2 nodes go down, I'm still safe, because 3 nodes will have the replica of my data. When it comes to writing, you may, it's serializable on partition threads. So like a put is let's say atomic for one key. So this is the main difference. We're going to see it with most or all of the NoSQL solutions we're going to look at. You don't have transactions like in a way you had in a RDBMS system. You normally can store something atomically, but only in the area, like, you know, for one key, under one key. You can't store 10 keys and have a transaction. You may do it using, like, you know, if you want some locking, if you want to be sure, oh, no put is overwritten by another put. Let's say you have 2 producers that are producing very, very quickly and may store something under the same key. You may do optimistic locking, which means, like, we know it from our RDBMS systems. We update if the value was, we know the previous value, and we update only if the value is still equal to the previous value that we know. But if we want to be 100% sure that our operation finishes, we don't want to have any mismatches, optimistic locking mismatches saying that, oh, the value has changed, we may use pessimistic locking. So you can also tune the consistency of your write, right? You may take it, and it's your decision. So what happens in the situation of a failover? We can see step number 1 in the left of the slide. We have, like, all the data. We have 3 nodes, and all of them are working. We have 1 backup. So on the right side of each node, we have a backup of some data. And now we can see in step number 2, node number 3 dies. It means that we lose the green data, the main data that were on node number 3. But the backup of this data, you see the green star, it's on node number 2. So it gets repartitioned, it gets rebalanced, the data are being recovered. And in the end, you can see in step number 3, node number 1 takes over and can serve the green data out of the box. It's not that easy because it won't be like this, that only one node will take this data. It will be rebalanced evenly, but for the purpose of the slide, it's pretty much okay to understand the mechanism. Yeah, so this is something that we also have in build. We're going to see it in different solutions too. What else do we have? So with normal RDBMS solutions, we had something that was called stored procedure, right? So we can send a procedure to the data in order to execute it on the database. Because otherwise, if we do it in Java, if we do it with, let's say, Hibernate and Java, as many people do it, it means that we select some data, we fetch, we do the transformation, we transform it to objects, we do all the serialization, we have it in our JVM, then we modify the data using objects, and then we send it back to the database. It's you have like serialization overhead, you have network transmission overhead. It takes a lot of time, and it's suboptimal. We want to be able to send the function to the data, right? So we want to say, hey, I know the data is on node number 1. I want to process the data on node number 1. I don't want to fetch it and then send it back. It's suboptimal, right? So you can do it in NoSQL solutions easily. There's something, for example, in Hazelcast, there's something called entry processor. It means that I'm implementing some logic, and I'm sending into the node. And if I have a couple of nodes, it's going to be sent to all of the nodes, right? So it's not like this that I'm fetching and synchronizing the data, not at all. I'm just sending the real logic, like Java logic, to my data in order to execute the logic locally, which is really, really cool. What other concepts are interesting when it comes to NoSQL solutions? So there's something called data affinity, which means that, let's say you have customers, and customers have orders, like a standard example, right? And one customer may have like n orders. So, and we want to see, let's say, we want to run a function saying, I want to, for each customer, I want to return the name of the customer and the number of transactions the customer has made, let's say, in the last 30 days, right? So if it was like this, that we had the customers or node number 1 and transactions, and all the transactions are on node number 2, it would be suboptimal, right? Because first we would have to take the customers, then we would have to fetch the data for each customer from the other node, which means, network hops, network latency, network overhead, serialization, and stuff like this. It costs a lot. So we may configure it like this, that our data is co-located. So for each customer, I may say I want to store the customer's transactions on the same node as the customer data, right? So when I'm accessing the customer, I may access the customer's data instantly because they are local. They are local for my node that I'm executing this business function. You use it using partition key. So for example, in this case, all the transactions or all the salaries, let's say, I do not partition them using the salary ID. I partition them using the customer ID so that all my data are stored together with the customer. It's really cool, and it's something that, with RDBMS, you would have to implement it by yourself. Here you have it out of the box. So the last thing that I want to show you is how you can query using like a key value store. It's not 100% true what I said, and it's normally about trade-offs and these decisions. So I told you that with a key value store, the database doesn't really understand what we are storing there. Yeah, that's true, but we may give the database some hints. Let's say with like a map, with a distributed map, IMAP, like with Hazelcast, it knows you are storing an object, right? You are storing a Java object. So you may say, hey, I'm storing like a person object, and the person object has a age field. So I'm executing a query saying, hey, I want the age field to be between 25 and 35. And let's say in this case, Hazelcast will use reflection. It will look at the object, it will look at the fields, it will find the fields, and it will create like a getter in order to fetch the field from you. So you may give some hints to the database in this case, but it's not like this that in order to do some querying and in order to tell the database, oh, I have these fields in this object, try to find them, and it happens automatically out of the box in Java using reflection. But yeah, as said, so by default the database doesn't understand the structure, but in this case we can use these hints, so to say, and we can run some normal queries like with SQL. Of course, we don't have joins, but we can do some predicates, and we may easily kind of fetch the data from our map using kind of query-like or criteria-like API, like in Hibernate or any other solution that you may probably know. Yep, so this was Hazelcast. This was one of the NoSQL solutions that I wanted to show you. It's used extensively. It's open source, Apache version 2 license. And let's say you may have a look at the projects, open source projects that are using Hazelcast internally, like Vertex or Apache Camel or MuleASB or all the other solutions that are listed here. So I encourage you to have a look at it. Yep, so we have to speed up. We have to have a look at another solution. Now we're looking at MongoDB, and this is now a document-oriented database. So it's something else. It's different than a key value store. And the main difference is that you store some documents that the database may understand. It understands them fully. It's not like this that we may give some hints. Hey, it's an object and I want an age property. The database understands the format of the document that you are storing. And in this case, it's like a JSON style document. I'm going to show it to you later on. You may store like max 16 megabyte documents because they say it's optimal for the database to do the sharding, replication, and stuff like this. Yeah, of course, you have some query language, and this is really cool here because you know, since the database understands the document fully, you may run a wide variety of queries because the database will simply look into the documents and and evaluate all your predicates accordingly. So one other thing about Mongo is that you store your data using in collections, so not tables but collections, and what's really cool here also, there's no schemas, or they say it's called dynamic schemas, but in practice it means there's not a schema. You don't really have to have the same documents in each collection. You may store totally different documents. Let's say a payment transaction in JSON and a customer in JSON having totally different fields. But in practice you wouldn't do it because, you know, what sense does it make? Then when you run your query, you have totally different data in your collection. But you may do it. You are not enforced like with RDBMS. So this is a document. At the top of the side you can see we want to store like fields A and B, MongoDB, and then a value of like an array of 2 elements in the attribute called B. And you have different ways of creating these documents, like a type-safe way is using SON or BSON document. You see it's a bit of typing. You may also rely on the type recognition by Mongo using the document object, and so this is the way you create a document. It's not 100%. It gives some overhead since you have to create a document that the database understands or may understand. So what's happened when we write the data? So we take a collection and we do like an insert. In this case, we do DB users, and then we insert a document, a similar document that we created in the previous slide. And as said earlier, you don't have any, atomicity on collection. You have an atomicity on single document. So meaning that if I want to update the same document from 2 clients, it's going to be atomic. But I can't do like a multi-document transaction saying that, oh, I'm updating this document and that document, and it's going to be atomic. It doesn't work like this. There are some tricks using isolated, but I don't want to go into the details. So when we query, it's also really cool. They of course they don't support a standard SQL language. You can't do joins since you are normally querying one collection. So when you do a query or querying single collection, you may do some nice tricks like projections that you do not return the whole object to you. So let's say you are selecting customers, you are checking something, and then you are returning the age of each customer only. So you don't have to, like in SQL, you must select one field. There's also like aggregations. So in order to enable you to do some more stuff than querying a single collection, you may do an aggregation. Aggregation is like kind of, you may imagine like a MapReduce flow, that you do something, you check something, then you reduce your stuff, and then in the end, you return some aggregated data. It's pretty cool. It's also in build. But what we want to look at right now is how do they solve the problems that we mentioned with RDBMS? How do they do replication? So it's like this, that you have primary and secondary nodes, so it's like a master-slave architecture. You have async replication, but it's in order to be consistent, you write to a primary node only. So you have async replication among primary and secondary, but you write to primary only. And then when it comes to reading, you may choose for yourself. So as said earlier, it's not that you may say that Mongo is always strictly consistent or it's eventually consistent because you have the choice. So it's pretty cool for you. Because if you read from the primary node, you're going to be strictly consistent, right? Because you can only write and read from the primary, so we are sure that when you have written something to the node and then you execute a read, you're going to see your data. If you don't care that the data may be slightly stale, you may read from the secondary node, so the green node, but the data will be eventually consistent, right? Because you have async replication, so it takes some time to replicate your writes to the secondary nodes, and in this case, the decision belongs to you. You may take the decision. Yep, so this was replication. Another interesting thing is sharding. Sharding means, we know what sharding means. We have already explained it. And in MongoDB, it's a bit different than in Hazelcast, as we've seen. You have some config servers, and the config servers actually are responsible for assigning the shards. They know where which shard stores which part of your data. So when you are in your app server and you're using Mongo and you want to query something, you have an entity called a router. Router will contact the config server on your get and will ask, hey, I want to get the data under key JFocus. And the config server will say, oh, so you have to contact the left shard number 1. But it's not like this that it's going to be happening all the time, because the router will cache this keys, this shard information, and if it gets a miss, let's say it contacts the shard and it doesn't have the data, then it contacts the config server again, because there might have been some migration that happened in between. So some nice mechanism in MongoDB too. So we have something called read preference. It means that when we do a read, as said, you may choose whether you are reading from primary or secondary, but it's not like this that it's also a binary decision, primary or secondary. You may say it's primary preferred, so if it's possible and then feasible, let's ask primary, but if no, it's going to be better to ask the secondary, you can ask the secondary. And also like nearest, which means it evaluates the latency and the hop time to the nearest node. And in this case, you don't know whether you're asking the primary or secondary, but you basically are asking the nearest node, so that your latency is smallest and your response time is the highest, right? So it gives you this flexibility. Another thing called write concern. It's also cool. So it's tunable again, right? We are always thinking about this tunability. We are owning the data, we are owning the application, and we want to basically be in charge of it. So in this case, when we write something to Mongo, we may say, hey, unacknowledged, so for like fire and forget. I'm just storing something, and I don't care if you have managed to written into a journal or not. And the other thing is that in acknowledge mode, it had managed to apply this data to the memory structure. So it managed to store this data in memory, but still Mongo hasn't written it to the journal. So if you have a power outage, you're going to lose your data because it's in memory, right? So it's going to be lost. In the third mode, it's journaled, meaning that it has been written to the disk, so I'm sure it's going to be there when I boot my server again. Use cases like mainly, I don't want to go into the details, you have to look for yourself what you like, but basically web apps, it's pretty popular with web apps because you're handling JSON, you're storing JSON, you're creating JSON, sending JSON to your JavaScript clients, and stuff like this, so it's pretty feasible to use Mongo in this case because it understands your JSON document, you may query out of the box in the JSON documents and stuff like this. Yep, so the third solution that you want to look at is totally different from the ones that we have analyzed. It's called Apache HBase. It's a big table store. There was a document, there's like a paper created by Google. Google's big table, it was running on Google's file system, distributed file system, and then open source solution followed, created on the Hadoop's file system. So what is a big table? Big table is basically something that we know maybe from relational databases. It looks like it, but it's totally different. I'm going to go into this in a second. It's column-oriented, so we do not store any documents, we do not store aggregates, like in Mongo, we do not store key and values, like in case of a key value store in Hazelcast. We are storing data in columns and rows. This is really cool. It's strongly consistent when it comes to a write on a single row, so pretty similar to all the solutions that I have already mentioned. But what is really cool, it offers automatic sharding, right? So it looks like we are using a table. A table is similar to like a RDBMS table, but when we store the data, they are being sharded out of the box. But what's a column-oriented or column family-oriented data store? It's a first difference in comparison to like a relational database. It's schema-less. You don't have a schema. It's not like this that you have to modify a schema of your table in order to store some data in it. The database doesn't care. It's so you may have one row that has columns from 1 to 100, and then you may have a second row that has like columns from 101 to 200. It doesn't really matter. Normally, like in a relational database, this is really important. The data is stored in such a way that it's like row-oriented. So I store one row, then I store the second row, and I store the third row. It's stored as rows, right? So let's say if I have 100 columns, and I want to select the data from the first column only from all the rows, I'm going to have to read all the rows anyway. I'll have to groom in memory all the rows and all the data. I'll have to read it to my buffer, and I'll have to process it, right? Because it's stored in rows. In this way, it's column-oriented in a way that each column family, as it's called, is stored separately. So I store the data in a columnar way. So let's say if I have a table with customers and their business transactions, if I want to fetch the customers only, so one column, I can just read one file. I don't have to groom all the columns. It's going to be very quick because I'm just fetching one column. Another thing is that it doesn't store, if I have some, let's say if I have a data, one row that has column A, B, and C, and if I'm storing another column, another row that has column D, E, F, it will not store empty values for the columns that already existed in the table. It doesn't really care. I may store any columns in the table, and it's up to me. So let's say if I want to store a list of elements, I may store each element in a single column. In a relational database, you would say, oh, it's crazy, you don't do it like this, you do a join, you have separate table, you have a couple of rows, and you store a collection. In this case, it's different, which is really cool. So it does the sharding for you. The table is divided into regions, so that if I store data, it's automatically out of the box divided into regions, meaning that, I'll have some data in one region, some data on another region, and I don't have to care about it. I just store my data, and it's sharded out of the box. It's done in such a way that we have a master. Master node assigns the regions and then does some load balancing and failover among the regions. And the region server is basically the server that's handling like read and write operations for us. So it's a pretty neat architecture. I'm not gonna go into the read-write details. It doesn't really matter. The most important thing for you is to know that if you store your data, it's gonna be distributed among the regions. Replication and sharding. Similarly to other solutions, in this case, like we have async replication. In Hazelcast, we could have sync or async. Here we have async replication. We can set the replication factor so that how many replicas we have on other nodes, and it's like this that if we read from the primary region, we know we're going to be reading strictly consistent data, so similarly to MongoDB, but we can also read from the secondary region, and in this case, it may be stale data since we have async replication, but the decision is up to us. We may take the decision, so it's pretty cool for us. So this is the thing that I mentioned. If we are reading with strong consistency, it's strong. If we are using with, it's called timeline consistency, then if we do a read, it will contact all the region servers, and the one that replies first is the one that will basically, the response will be get by the client. What are the use cases? There's a lot of pretty cool use cases. You can have a look at it. So for example, Facebook uses HBase for messaging. So if you're writing messages to your friend or Facebook, it's being stored in an HBase. Yeah, it offers you pretty strong consistency, and you can configure it like this, that you have low latency, random reads, and stuff like this. But what's really cool for you is that if you have a table and you want to switch to something that's sharded and distributed and offers you all the mechanism that we have just mentioned of NoSQL solutions, you may use HBase, and you know it will be kind of like a bit more similar to you than switching to another type of store. So the last database that we want to look at is called Cassandra. Its concept is similar to HBase. So Cassandra, basically Amazon created a paper that's called DYNAMO, and they're like, okay, we like the concept of HBase, we like the concept of this column family store, we like this columnar things and stuff like this, storing the column families in separate files, but we don't like the fact that we have this primary and secondary servers. We don't like the region servers. We want to have like a ring of servers. We want to have a master-master architecture so that I may write to any node and read from any node. And they created kind of like a combination of the big table concept and like a master-master peer-to-peer concept of architecture. And that's the way how Cassandra got created. It's basically big table plus this DYNAMO paper. It offers you incremental scalability because since it's like master-master, you may add nodes like, you know, without any limits to your architecture, and the idea is that it's going to scale in a linear way, because the more nodes you have, the more nodes can handle your read or writes. This was the main concept. I can read from any node and write to any node. How does it work? It works like this, that we have this master-master architecture, all nodes are interconnected, and we have a coordinator. So if I ask for a specific row or key, the coordinator will ask the nodes that are responsible for it. Let us have a look at the replication factor. So it works like this, that you may specify on how many nodes you want to store your data. So this is the number of replicas you're going to be storing your data on. And if I set it to 1, I'm going to be storing the data on 1 node only. If I set it to 3, like in this case, you see the data will be stored on 3 nodes in Cassandra, which is really cool. Consistency level, this is really cool because then you have like read operations and write operations, and you may choose on which consistency level you want to do it. We just said, oh, I had a replication factor of 3, so I'm going to be storing my data on 3 nodes. But when I do the read or when I do the write, I may say, yeah, I know I'm supposed to store the data on 3 nodes, but this write has to be really quick. So I want my operation to return after the data is written to 1 node, and it's going to be replicated asynchronously to the other 2 nodes that is supposed to be stored. But I don't have to wait for it. I don't want to wait for it. So this is really cool. The same may happen to your read operation. You may say, oh, I know you store the data on 3 nodes, but I want the read to be really quick, so I don't want to wait for checking like whether the data, like to getting the data for 3 nodes. I'm just getting the data from 1 node, and I'm not waiting if it's strictly consistent. So I'm not waiting for the response from the other 2 nodes. So this is pretty cool. This is tunable by choosing the consistency level and read and the replication factor and consistency level. You may tune your reads and writes in a way that you want to. So either it's going to be slow, but you are sure it's going to be written to 3 nodes, and I'm going to be reading from 3 nodes, or it's going to be quick, so I'm just writing to 1 node or reading from 1 node. But it may be that my data are stale, or it may be that something crashed because I haven't managed to write everything, right? So that's pretty much it that I have prepared for you today. These are the 4 databases that I wanted to mention. Let me go to the last slide. The last thing that I want to say is that these solutions are not a Swiss Army knife, right? We've seen that there are a couple of solutions, they have a couple of mechanisms that are in build. Some of them are more interesting, some of them are less interesting. But the thing that I want you to remember after this session is that you own your data, you own your applications, you know your use case, you know your conditions or requirements that you have to fulfill when it comes to latency and throughput and stuff like this. So there's no solution, like one fits all solution, right? You have to choose for yourself. You have to see, oh, for this table, it has to be strictly consistent, so I'm going to use this mechanism. for this table or for this store, I don't need it, so I'm about latency and stuff like this, so I don't need something that's strictly consistent, but I can release some of the conditions, right? So I encourage you to evaluate these solutions and have a look at them and see whether they would work for you. Thank you very much.
Love